Bonjour et merci. This is Mark Andreessen, one of the pioneers of the internet, who's now an investor. And the way he looks at the world is he looks at different business sectors and say, how can we reinvent it, knowing that software can play such an important role? What does he mean by that? Well, we've had big companies like this whose fortunes have declined as they've been replaced by companies like this, and the difference is software. That these companies are run on software. We have even companies that you think of as being in the physical world, like Walmart. It's really a software network, and that's where they gain their power. Once we go beyond software, we ask, what's next? And here's a new generation of individuals who are starting new companies who are trying to reinvent the world based on machine learning rather than on traditional software. Can we move faster? Can we reinvent faster? Can we disrupt faster by using machine learning techniques rather than traditional software techniques? That's what I want to explore today. So they could well be asking, although this isn't a direct quote, how can we reinvent it knowing that machine learning can play such an important role? We can invent brand new classes of applications. One of those is visual object recognition. So I'm a photographer, I collect lots of photos, and I spent hours and hours and hours organizing them and putting them into little folders and putting keywords on them. It took up a lot of time. Now we can disrupt all that. This is Google Photos, so I threw all my photos in there. I didn't do any tagging or anything else, and it did it all for me. So it's identified some classes: birds, lions, flowers, Legos, sky, lizards, and there were more. It did this all by itself. I didn't have to do any work. I can also drill down, be more specific. I can find pelicans. I can find clematis, though you see it made one mistake there in the upper right. That's not actually a clematis, so it's not perfect yet. Sunsets, it's really good at that. Clouds, finds lots of pictures with clouds, very accurate there. And even things that I wouldn't really expect. So I would never have labeled my photos by nose, but when I searched by nose, it picked out some interesting and prominent examples there with the sea lion and the tapir and the rhino and so on. So this is sort of done away with all this work I had to do and done it automatically. And how can we build systems that can do things like this? Well, in the traditional software model, we have a programmer. They create a bunch of rules. They write them down. They try to get all the rules right. It's hard to do right because there's complexity. In the machine learning model, it's not a programmer that writes the program. It's a machine that writes the program. And how does a machine know to write the program? Through data. You show it lots of examples. You give it a model that says, this is what I think the world is like. And then you tell the system, arrange it so that in the future, you'll do things similar to the examples you saw in the past. And then out comes what's mostly a black box. So you give examples in. What comes out is a program that will do the right thing. You're not quite sure exactly how it works, but it's a black box with a lid that's open because we can peer inside it. And one of the big challenges now is how do you peer inside and how do you understand what's been written by this machine intelligence as opposed to, in the past, we had better means of understanding what was written by a human programmer. Let me give you an example, the task of spelling correction. So if you use one of the popular word processors, you're familiar with this, you're writing along, and you get the little red squiggly lines. And sometimes it's very helpful when you make a spelling error. Here, it was not so helpful. So I've correctly spelled the name of my colleague here, but he still gets the little red squiggly lines under his name. And the reason is because his name is not in the dictionary. And this was programmed by following a dictionary. And if you took the advice of these traditional programmers who followed the dictionary, you would replace his name, Mehran Sahami, with the suggestions, Tehran Salami. Not a good suggestion as far as I know. Salami is not a major export of Tehran. But if you had to find words that were in the dictionary, that's probably about the best you could do. And how did the programmers come up with that? Well, they had the dictionary, and they wrote lots of individual words like this, or individual rules, and carefully wrote and debugged them. Here's a different open source spelling correction program, and I won't go over it, but it's about 2,000 lines of code. And notice that's just for English. So if I wanted to do it again for French, I'd probably need another 2,000 lines. If I wanted to do it for a language that was very different, Finnish or a different character set, Arabic or Chinese, I'd have to start over from scratch. So a lot of work to get this done. Compare that to what's done if you go to search engines these days, rather than to word processors. They always get it right. So they know who Mehran is. They even show you pictures and correctly identify it if you typed it right, and correct it if you got it wrong. How do they do that? It's because they're built on examples, not from dictionaries. They're built on examples of all the words they've seen on the web, and examples of all the users that come and correct the spelling from one moment to the next. And to make a system like this, you make a model. And the model can be as simple as this one sentence that says the best word is probably a word that's very likely in English, and a word that's very close to what was typed. You can build an entire system here in 20 lines of code rather than 2,000, and note that that's total, that I could reapply this to English or to French equally well. All I need is examples of good spelling in English or French, and I'm done. So that seems like an amazing panacea, 100-fold at least increase in productivity, and it's great and it allows amazing new things, but there is no free lunch. So why now? Why are we suddenly seeing this increase in machine learning? I think it's mainly because we have the computing capability now that we didn't have before, and because so much of the information that's out there in the world is now available in digital form as data. And so we're operating at the scale of billions to trillions of data points, millions to billions of features, of aspects of the world for each data point, and operating in data centers with hundreds of thousands of CPUs, and so on. So operating at a large scale. Now, let's talk about this task of object recognition. How do we know that there was a lion or a sky or clouds in a picture? And if we want to do this with traditional software engineering, we'd very laboriously come up with models one object at a time. So here, somebody's trying to make the model for pandas, and they build this 3D model, and they write a lot of code. And a few months later, maybe you can recognize pandas. But if you want to recognize hundreds of thousands of different objects, that's just not going to cut it. We need a new approach. So the first thing we tackled about a decade ago was object recognition via supervised machine learning. And what we're starting to get into here, and we're here in the Louvre, so I had to show some paintings. We're getting into this fundamental distinction between rationalism and empiricism. So the rationalist, the traditional programmer, says, I can understand the world, and I can write down logical rules that describe it. The empiricists, like Hume, say what we see in the world is what determines what's normal, and we don't have to understand all the rules. We follow custom. So in a supervised approach, we go out and we gather a lot of pictures with labels on them. So here, we gather a lot of pictures of pandas that have the word panda associated with them, and then just to see something else, here's a bunch of pictures of gibbons. I've represented schematically the pandas by the green dots and the gibbons by the red dots, and then we ask the computer to draw a line that separates them as best it can, and we see here it's done that. Now, if we get a new photo that we've never seen before, if it's on the right-hand side of the line, then we say it's a panda. If it's on the left-hand side, we say it's a gibbon. And maybe there are other parts of the space as well. So that seems to work pretty well. The problem is you have to get the pictures with the labels on them, and that can be expensive. You have to ask somebody to what's the correct answer for each of these pictures. So the next step was to do it via unsupervised machine learning. So by unsupervised, I mean we just take all the pictures we can find, we throw them in, and we ask the computer, you make sense of it. You figure out what's in there. Is there such a thing as a panda? If there is, you go ahead and represent it. How could a computer possibly do that? Well, I could explain it in math, but I decided instead to explain it in terms of a parable. So imagine your business is selling these kitchen tile sets, and you have a nice catalog of beautiful scenes like this that your customers can order. The business is going great. But you get the idea you'd like to modernize. You'd like the customer to be able to upload a picture, and then you'll make the tiles, ship them out to them. They'll have the beautiful backdrop for their kitchen. But it turns out that's very expensive, because now you're making the tiles in batches of one at a time, and it's much cheaper to make them in larger batches. So what you'd like to do is have an inventory of tiles. The user comes in, uploads their picture, you go into inventory, find each of the individual tiles that are close enough to their picture. It doesn't have to be exact. Assemble those and ship those out. So the question then becomes, what tiles go in the inventory? And that's basically the answer to this empiricist question of what is the world like? This is a representation of everything that's out there in the world. So we go back to the pictures, we see what's in the pictures, and I promise this is the only slide with math in it. We try to come up with, say, we're going to limit ourselves to a certain number of pieces in inventory, say 1,000. Doesn't really matter what the number is. And we try to choose those pieces such that we can reproduce all the pictures with a minimum difference between the copy and the image. And here I'm actually cheating a little bit. I said I was making kitchen tiles, but now let's think of it more like stained glass windows, because you're actually allowed to superimpose a couple different pieces at the same place. So it's like having several pieces of stained glass in the same location. And the answer to that question should be a representation of all the stuff that's important in the world. If I can represent any picture that I've seen before or any new one with these pieces, then these pieces must be important. So what does the inventory look like? Well, this was done for the first time. It was very exciting to say, what's going to come out? What's the world made out of? And the answer turned out to be not so exciting. That when you do this, you do the math, and you do all the calculations, and it comes out that the world is made out of lines, which is a discovery that's made by any kindergartner with a pencil or a crayon. They know they can draw anything with lines. So that was disappointing, but we didn't give up then. We went back and said, oops, having trouble advancing here. We said, okay, so if we just make one inventory, it comes out as lines. Anything can be made out of lines. But what if we said we're going to have one inventory, maybe that's going to be lines, and then we're going to try to build up the next piece out of that. So take these small lines, build them up into larger pieces, and then take those and build them up into larger pieces still. What happens if you define the math to do that? And now for the first time, you get something interesting. So the first inventory is still lines. The second, if you feed in faces as examples, it actually identifies that eyes and nose and mouth are important parts of the world, and that faces are important parts of the world. If you feed in cars, it identifies that wheels and doors and so on are parts of the world and so on. So for the first time, we have a computer that's breaking the world down into pieces entirely on its own. Didn't have to tell it anything about what the world was like, just show it lots of examples, and it breaks the world up into coherent pieces. So very exciting. We did an experiment. We gave it 10 million YouTube video frames. We'd like to do the full videos, but as a first experiment, just pick out one frame from each one. This was about 100 times larger experiment than anyone else had done at the time. Since then, other groups have also joined in, and there's been a lot of great progress. So if YouTube videos come in, what does it find? Well, it finds the world is made up out of cats. And many other things as well. But one of the pieces out of those 1,000 pieces at the top level was dedicated to cats. And it could recognize all these as being cats. And if you asked it, what's the best possible cat, you have to squint your eyes a little, but that's sort of the mathematical answer to what the best possible cat is. So it's able to do this all on its own. There's a competition that's run every couple of years for people in this field, in which you try to identify pictures and classify them into one of 20,000 different categories. There's 300 different categories of fungus. So I would be terrible about this. I know about 5 different categories of fungus, so I could not pass this test, but computers do pretty well at it. Here's some example of some of the easiest and hardest classes for computers to recognize. And it's interesting, right? So computers do 100% on Blenheim Spaniel. I hadn't even heard of that one before, but apparently they're distinctive. But computers don't do as well for things that have more variation, like water bottles, which can be many different sizes and shapes. They're only 68% accurate on those. And this is what it looks like. So there's multiple levels of inventory there. This is a team from Toronto. In 2012, they scored 16% errors on identifying out of these 20,000 classes. And then the 2014 model got down to a little over 6% error, and it keeps on improving. So very exciting progress of getting something from nothing. Just showing the system a lot of pictures, and it automatically figures out what the classes are, figures out what the world is made out of. Now, let's go one step further. So I talked about a very trivial part of language, spelling correction, and there's lots of other work that's done in language. And I talked about understanding images. Can we put those together? Can we show the system a bunch of examples of captions and pictures, and then give it a new picture and say, what's a good caption for this? So the system both has to understand the world, understand all the stuff that's in the world. It has to understand what's worth talking about, what's important enough to go into the caption, and it has to understand the rules of the language, in this case English, well enough to generate a caption that seems coherent. So here's an example. Here's this picture. We asked a human, what do you think is a good caption for that? And said 3 different types of pizza on top of a stove. You have to look carefully to say, oh yeah, there are 2 different types of pizza on the left there. And then we asked our first computer model what the good caption should be. And it said 2 pizzas sitting on top of a stovetop oven. So it's not quite as attuned to the difference between the tomato and the mushroom there. And then we did a second model, and it came up with a pizza sitting on top of a pan on top of a stove. Okay, so think of what it's doing here. Out of just showing it examples, it's come up with a model of the world and a model of English, and doing a pretty good job. Now, I don't want to say that it always gets it right. So I'll show you some of the outtakes. So here's an unusual image, a horse in pajamas. I guarantee you there had been no training examples of horses in pajamas, and so it did the best it could, and it said a couple of giraffes standing next to each other. And maybe that makes a little sense, because the spots on the pajamas do look a little bit like reticulated giraffe spots. Here's one. A reflection of a dog in a side view mirror. And here's the king. And it thought that was a man riding a skateboard. Apparently, it had never seen anybody try to dance in quite that type of pose before. And I don't know if you can quite see it here on the projector, but there actually are horizontal lines along the bottom there that might look a little bit like the lines of a skateboard. No wheels on the skateboard, though. Okay, so it's not perfect yet, but tantalizing in what it can come up with. So what are some of the challenges for machine learning systems? So here's a very interesting paper about adversarial examples. So by that I mean, if we tried to trick the system, what could we do? So again, here's sort of schematically, here's a picture of a panda, and it's near this decision boundary between panda and gibbon. What if we just sort of tweaked the picture as little as we could to just barely push it over the decision boundary? And then we would we fool the system, or would it correctly figure it out? So we take the picture for panda, we head in the direction of the boundary, and heading in that direction comes up with this bunch of pixels here that look like noise. And then we took just a tiny bit of the noise and added it into the panda. We get a picture that looks indistinguishable. So it still looks exactly like a panda, but now the system says gibbon, and it says it with 99.3% confidence. So we've completely fooled the system with something that a human would say, well, not only would I not say that's a gibbon, I can't even tell the difference between those 2 pictures. And so what did we learn from this? Well, we sort of, or at least I thought coming in, maybe people more experienced, you heard about Jan LeCun yesterday if you were here. He may be well ahead of me on this. But I thought we had sort of broken up the world into this. We had sort of these large chunks of islands, of spaces with borders in between them. But I no longer think that's true. I think instead what we have is we have tiny little filaments where we know what's going on. And in between them is this unexplored space where here be monsters, and the system has no idea what's going on in between these tiny little spaces that are labeled with pictures. Of course, humans also make these types of mistakes, so we shouldn't blame these machines for making silly mistakes with the panda when humans have their own problem. Another paper we published recently says machine learning is a high-interest credit card of technical debt. So technical debt is this notion that over time, as you're developing your software, if you're going really fast, you may be getting stuff done, but you're contributing to maintenance problems that have to be paid down later on. And the idea here is, yes, machine learning allows you to go really, really fast, right? We can write 100 times less code and go 100 times faster. But that means we're accumulating the debt faster as well. So what are some examples of that? So one is lack of clear abstraction barriers. So if you write traditional code, you've got little modules and subroutines and so on, and you can say, if there's a bug, I know it's going to be in this module. With machine learning, if there's a bug, it could be anywhere. You don't know how to identify it. If you change anything, then everything changes. Like in this Pichincho machine, you change one little knob and all the balls fall in different places. Much more so than with traditional software. There are feedback loops. So here you do a search, you get some results, you click on the results, and if we have a system where part of the input is the click on the results, then the results depend on the clicks, but the clicks depend on the results. And there are ways of dealing with these feedback loops, but we have to understand how they work. There's this notion of an attractive nuisance. So one group develops this set of what they call synonyms that says, hey, for our application, when you use this word, you could replace it with this other word. And another group within the company says, that sounds great. I have a different application. I want synonyms too. But it may be that synonyms are always with respect to a purpose. There's no such thing as an absolute synonym. There's only a synonym with respect to a specific purpose. And it may seem like it's going to be good, but in fact, it may be going in the wrong direction. There's data dependencies can be harder to debug than code dependencies, so we squished down the size of the code to be much smaller, but we've increased the size of the data. And our whole tool set for doing software development is kind of based on understanding code, not on understanding data. And we aren't geared up with all the automated tools and test suites and so on to deal where we mainly have data and configuration dependencies and how we put the data together. And that can all be fixed, but we need to get all the tool sets. There's this thing called the optimizer's curse, which says, if I try 30 different variations of my algorithm and then choose the best one and go ahead and deploy that, this curve here tells you how bad that estimate's going to be. So basically, if I chose the best out of my 30 different machine learning experiments, I made the best choice I could, but the one I chose is best in part because it was good, but also probably in part because I was a little bit lucky. And so I shouldn't change my decision, but I should expect that when I deploy it, that it's probably going to do worse than it did in the test, because part of the reason it won the test was because it's lucky, and in real life it will no longer continue to be lucky. There's the allure of standard packages. We have some really great open source software that does all this amazing stuff. And people build huge pipelines on top of it. And the software helps you get started really fast, but then the problem is you kind of get stuck and you kind of get locked in. And in the end, machine learning ends up being like 5% of the total amount of software you wrote anyways. So you might be better off starting from scratch and rolling your own rather than sticking with the packages. There's this idea of non-stationarity, which means things change over time. The data you had before, some of it's still good, but some of it is becoming stale and old. And we need methodologies for knowing how to deal with that, how to replace the old. And finally, there's this idea of lack of intuition, that we still don't really understand everything that's going on with these complex machine learning systems. So what is this? So this was an example done at Google. We call this the Inception Project. And there was a picture of a country scene with trees and a river flowing through it. And then we told our neural network, which was good at recognizing objects, so it could pick out, here's a tree and here's a river. We said, we're going to feed back into you the notion of animal. So we say, go into this picture, see if you can find any animals, and then add those back into the picture. And this is what it comes up with. So it hallucinates birds and dogs, and it adds eyes everywhere, so every knot of the tree becomes an eye of an animal. And this has poetically been thought of as what androids dream of. I don't know if that's really the right way to think of it, but it's one way to explore what it is that these networks are seeing. And we need better tools for understanding that and knowing where we're going. Okay, so why don't I stop now and open it up for the questions.